Today we are going to look at finding limits algebraically. This lesson is meant to be a continuation of the first lesson called A Graphical Approach to Limits. If you have not watched the first video about the graphical approach, please go back and watch that now. You can also find that on my website before continuing with this one. Today we're going to determine limits without the benefit of looking at a graph. So finding the limit as x approaches a, some number of f of x, the first step to try is to plug in the value a. Let's revisit that first example we did in the last video. Suppose we wanted to find the limit as x approaches 2 of f of x. The first step is to try to plug in 2. If we were to do that in this function, however, we run into a problem. If x is 2, that makes our denominator 0. Because that didn't work, we have to continue with the next step, which is to factor and cancel, and then go back to step 1. See if you can plug in your x value. Yesterday we saw that we could factor the numerator. It's a difference of cubes, and so it factors like this. Sure enough, we have a common factor of x minus 2 that can be canceled, leaving us with this. If we then try to plug in the x value of 2, we get 2 squared plus 2 times 2 plus 4. 4 plus 4 plus 4 equals our limit value of 12. And we can see that on the graph. It looks like the y value is at 12, and this was also the one that we plugged into our calculator. And remember, we saw, sure enough, the y values were getting closer and closer to 12 on either side. The last possibility is that the limit could be equal to infinity, negative infinity, or perhaps not exist at all. We will talk more about that third option here in a few minutes. The first 4 examples, we will be able to use steps 1 and 2. Alright, so example 1. Suppose we want to find the limit as x approaches negative 2 of this function. It looks like a polynomial. We can do this by simply plugging in negative 2. And when we simplify, we get 13. So our limit is equal to 13 on our graph at x equals negative 2. The y value would be 13. This is a point that would be on the graph of that function. Second example, we're looking at the limit as x approaches negative 2 again. Now we're looking at a rational function, but we could also do this by just plugging it in. So we end up with negative 10 divided by negative 4, which would be equal to positive 2.5. In the next one, looking at the limit as x approaches negative 2, if we try to plug it in, we end up with getting 0 over 0, which is no good. So we're going to attempt to factor and then cancel. Let's factor our numerator into x minus 4 times x plus 2, and we'll factor our denominator into x plus 2, x minus 2. So sure enough, we can cancel the common factor of x plus 2. Now we're going to go back to step 1 and plug in our x value of negative 2. So on our numerator, we have negative 2 minus 4 over negative 2 minus 2, altogether giving us negative 6 over negative 4, which will simplify down to positive 3/2. In the fourth example, again, if you were to plug in our value, this time we're looking at the limit as x approaches 1, we end up getting 0 over 0. So again, we're going to attempt to factor and then cancel. If we factor this numerator, we get x minus 1 over x minus 1. The denominator is another difference of cubes, similar to what we had over here. And if you remember the formula for factoring a sum or difference of cubes, in this case it's a difference, so we can think of it as being a cubed minus b cubed. Our first factor is a minus b. Then we have a squared plus ab plus b squared. So in our problem, a would be x and b is 1 because 1 squared is the same thing as 1. So we'll factor it into x minus 1 times x squared plus 1x plus 1 squared. We'll go ahead and cancel a common factor of x minus 1. And now let's see if we can successfully plug in the x value of 1. So on the numerator, we get 1 minus 1. Our denominator, 1 squared plus 1 plus 1. So this is okay because we end up with 0 over 3. It's okay to have a 0 in the numerator. It just means the entire thing is equal to 0. One other situation that you might encounter is finding the limit as x approaches some number of a constant function. A constant function does not involve a variable. So for example, the limit as x approaches 3 of 10 will always be equal to whatever that constant value is. Will always be equal to 10. If you think about the graph of the line y equals 10, it's a horizontal line passing through that y value. So no matter what the x value is, this will always be the y value. Now we're going to talk about that third situation. So if steps 1 and 2 do not work, meaning that you have a 0 in the denominator, your answer is going to be one of the following. It will be positive infinity, negative infinity, or does not exist. To determine which, you must split your limit into two separate limits. The limit as x approaches a from the left side and the limit as x approaches a from the right side. We're going to make a sign chart, which I'll show you how to do by plugging in a number close to a on the left side and determining its sign. You will also plug in a number close to a on the right side and determine its sign. Each of these will be some form of infinity, either positive or negative. Only if they are the same will the limit be infinity or negative infinity. If they are not the same, we'll say that our limit does not exist. What this says is that in the case of limit as x approaches a from the left, some form of infinity from the right is also some form of infinity. We'll need to check to see whether they are the same. All right, so let's look at our function in this next example. So we see step 1, plugging it in doesn't work because we get a denominator of 0. Step 2, it's not possible to do any factoring or canceling. So our answer must be one of these. Now, sometimes it's helpful to think about what the graph of the function would look like, especially since now we've had some practice of finding limits graphically. It's a rational function. We know that there's going to be a vertical asymptote at x equals 2, and there will be a horizontal asymptote at y equals 2. So the degree of the top is the same as the degree of the bottom. So the horizontal asymptote equation is y equals a over b, the ratio of the leading coefficients, 2 over 1. So let's just think about what that graph would look like. If we were to sketch a vertical asymptote at 2, we'll do a horizontal asymptote at 2. And we're interested in knowing the limit. What are the y values approaching as x approaches 2, which is going to be right here. So we know that there's two ways that the curve of a rational function graph can approach an asymptote. So it could either be approaching it upwards, like this, on either side, or it could be approaching it downwards. So we need to see if it's the same on both sides or if it's different. So we will make a sign chart. We'll start by plugging in an x value that is on the left of 2, so something like 1.99. So we're interested in what's happening right here. If we were to think about plugging that in, we're only interested in the sign of our final answer. We need to know if it's going to be positive or negative. So the numerator will end up being positive. 1.99, take away 2. 2 is a little bigger, so it's going to go into the negatives. And a positive divided by a negative is a negative. So that tells us that it's going to be going down on this side. Now we're going to test an x value on the other side, a little bigger than 2, something like 2.01. It will still be positive on the top it will also be positive on the bottom, so a positive divided by a positive is a positive. So this tells us that our curve will be going upwards as it approaches 2 from the right side. So visually we can see here the limit definitely does not exist because we're not approaching the same direction. And so that will be our final answer for this limit in example 5. In the next example, we see it's another situation where step 1 and step 2 don't work, so our answer will be one of these three. We're going to make a sign chart again to figure out which one it is. So this time our limit is, we're interested in finding the limit as x approaches 0. So if we think about the limit as x approaches 0 from the right side, we want to choose an x value that's slightly above 0, something like 0.01. If we were to plug that in, 4 over 0.01 squared, the sign of the numerator is positive, the sign of the denominator is also positive, so altogether it's positive. Finding the limit as x approaches 0 from the left side, we want to choose an x value that's just below 0, so we could do negative 0.01. And if we think about plugging that in, a negative number squared is still positive. So again, we have a positive divided by a positive, giving us positive. Because these are the same, that means that our graph should be approaching positive infinity on either side of x equals 0, and so that means that our limit answer is positive infinity. In example 7, we will see that step 1, plugging it in, will result in a denominator of 0. And so if we try step 2, let's see what happens if we try to factor this. So on our numerator, we could factor this into x plus 3 times x minus 1. Our denominator would be x plus 3 times x plus 3. So we're actually able to cancel that common factor of x plus 3. So here we have a factored form, but the limit as x approaches negative 3, it still doesn't work to plug it in because negative 3 plus 3 still gives us a denominator of 0. So we have to move on to step 3 again. We're interested in knowing what's happening to the y values as x approaches negative 3 from either side. So let's first think about what happens as x approaches negative 3 from the right side. So we're going to choose an x value that's a little bit bigger than negative 3, so we could choose negative 2.99. If we plugged it in here to kind of the more simplified form, we could think of it as being negative 2.99 minus 1, which is going to be negative, over negative 2.99 plus 3, which is going to be positive. Altogether, a negative divided by a positive is a negative. So that tells us that our graph is going to be approaching negative infinity as x approaches negative 3 from the right side. Now we'll need to think about what's happening as x approaches negative 3 from the left side. So we'll want to choose an x value that's a little bit below negative 3, something like negative 3.01. If we plug that into our function, the numerator will be negative. The denominator will also be negative. A negative divided by a negative equals a positive. So that tells us that our graph is going to be going upwards, approaching positive infinity as we approach negative 3 from the left side. So because these two are not the same, that means that our limit does not exist. All right, let's look at example 8. First off, if we try to plug in The x value of 2, that's going to give us a denominator of 0. If you do a quick check with the numbers, 2 cubed is 8. 8 minus 8 will go to 0. Over here, 2 squared is 4 times negative 6 will be negative 24. Plus 12 times 2, that'll be positive 24. So everything is going to cancel. We could think about factoring the numerator by taking out a common factor of 2. However, the denominator is not easily factorable using a factoring strategy, although there are 4 terms. If we try to do factor by grouping doesn't work here. But what we can do, we know that when we plug in 2 into the denominator, it makes it 0, meaning that 2 is a 0 of this polynomial, and that means that x minus 2 is a factor. So if we divide our denominator by x minus 2, that will give us a factored form of that denominator. We can do synthetic division. And we should get a remainder of 0 because we know that x minus 2 should be a perfect factor. All right, so let's go ahead and write this out in our denominator. So one of our factors is x minus 2. That's what we divided by. Looking at the numbers here on the bottom row, we have 1x squared minus 4x plus 4. Let's go ahead and cancel the common factor of x minus 2. We could actually continue factoring this denominator, writing it as x minus 2 times x minus 2. Now, we still cannot plug in the x value of 2. It's still going to make our denominator equal to 0. So we need to move on to the third step to figure out, okay, is it positive infinity, negative infinity, or does not exist? So we'll do a sign chart again. Testing a value that's a little bit less than 2 will tell us the limit as x approaches 2 from the left-hand side. So we can think about it like this. So 1.99 take away 2. 2 is bigger, and so that's going to be negative. This is also negative. So a negative times a negative will be a positive. 2, of course, is positive. Positive divided by a positive will equal positive. So that tells us that the limit as x approaches 2 from the left side is positive infinity. Now we'll test a number on the other side to see the limit as x approaches 2 from the right-hand side. So let's actually change this to the 2.01. Sorry, that menu keeps showing up every time I change it from pen to eraser or whatever. I don't know how to make it stop. Okay. See, that's annoying. Okay, so let's think about this again. So obviously our numerator is still positive on our denominator, so this little part will be positive multiplied by another positive. Positive over positive is positive again. Great, so because they are the same sign, that tells us that our limit is going to be positive infinity. Let's take a look at example 9. Notice how this function looks a little different from the others. There are 2 parts to it because this is a piecewise function. Now, I've drawn the graph here just to help us remember and understand what a piecewise function notation really represents, but the goal is for you to be able to do this algebraically without having to draw the graph. So a reminder of what this means. It's telling us that our function curve will be shown by the line x squared minus 4 for all x values that are greater than or equal to 1. So on the right-hand side of x equals 1, I'm actually going to draw in a vertical line here at x equals 1. You could think of that as being like a boundary line separating the 2 sides. So on the right-hand side, that's where x values are greater than or equal to 1. This is going to be a parabola shape that's shifted down 4 units. And so the vertex of the x squared is at 0, 0. The vertex, when you move it down 4, is going to be down here at 0, negative 4. But I didn't plot that point because it's on the opposite side of where we want that graph to show up. So if you think about the vertex being here of our parabola, it kind of makes our full shape. The other side of the parabola would look like this. So from our vertex, we could get 2 more points, going over 1, up 1, and then over 2, up 4. So remember, that's sort of the general pattern of points for a basically half of a parabola. And so I have a filled in circle here, so that's to go here with the blue line, because that's for x values greater than or equal to 1. So the filled in circle will be here. Now on the left side, that's where x values are less than 1. So I'm going to write this over here. And the graph on that side is going to be defined by the line negative 2x minus 1. So think that it has a y-intercept at negative 1. We're going to go up 2, over 1. Oops, this point is wrong. It's supposed to be up 2 over 1 again. That was actually up 1 over 1. So we'll pretend like we went up 2 over 1. And if we continue that pattern this way, we can go down 2 over 1 in this direction. So that's that line. But notice how with the black line, I just did a big open circle because that's for any x value less than 1, but not including 1. We don't want there to be any overlap where we would have 2 points in the same place, and so that's why this one is strictly less than and this one is greater than or equal to. But what's interesting is that they happen to end up being at the same y value. So now if we think about finding the limit, it wants us to find the limit as x approaches 1. Well, as x approaches 1 from the left side, the y value is negative 3, approaching negative 3. As x approaches 1 from the right side, the y value is also negative 3. So the limit exists, and it is negative 3. Now let's talk about how we could do this algebraically. We could try that first step of just simply plugging in the x value of 1, the limit as x approaches 1, and we'll want to do that in both functions to see if it is in fact ending up in the same place for both functions, and sure enough the numbers work out. So that's how you can do it without looking at the graph. Just plug it into both and see if it ends up being the same thing, and that will be your limit. Okay, now example 10 is another piecewise function, but this one is a little bit more complicated because the pieces are rational functions. Notice how the first possibility, we're looking for the limit as x approaches 2 of just plugging in 2 doesn't work because that's going to give us a denominator of 0. The second step of trying to do any factoring to cancel also will not work, and so this is going to be a situation where it's either infinity, negative infinity, or does not exist. So we'll need to make a sign chart. First, let's look at what happens as the limit approaches 2 from the left side. So we'll be looking at an x value that's a little bit less than 2. That's on the left. Now for x equals 1.99, we need to plug it into the bottom function because that's the function that we'll be using for any x value that's less than 2. So on the left side of 2. If we plug it in, we have 1.99 minus 3 over 1.99 minus 2. So it's going to end up being negative over negative. Negative divided by a negative is a positive. So that tells us that our graph is going to be approaching positive infinity from the left side. Now from the right side, we'll test an x value that's a little bit greater than 2, so something like 2.01. Oops, hold on. Okay. We are not going to plug it into that same bottom function as we did before because x is greater than 2, and so we're going to need to plug it into this function rule. So we will have 2.01 over 2.01 minus 2. So we have a positive divided by a positive. Overall, that will equal a positive. So it's telling us that our graph is also approaching positive infinity. It's going upwards as x gets closer to 2 from the right side. So because these are the same, we can say that our limit approaches positive infinity. Now, if you want to make a note in your packet here, we have now completed enough of the in-class examples to do problem numbers 1 through 24 on the homework assignment. There's one final section left with a few more examples, and that will help us with the rest of the homework assignment, number 28 through 36. So the last type of problem we're going to look at in this section are in the type of a limit as x approaches positive infinity or a limit as x approaches negative infinity. So if we think about what's going on here, as the limit as x approaches infinity, whatever's going on in our graph, we're thinking about what's happening on the far right side as our x values are getting bigger and bigger, or as x approaches negative infinity, what's happening on the far left side as our x values get smaller and smaller. There's a list of rules here that are going to be very similar to the rules for deciding the horizontal asymptote when graphing a rational function. Because if you think about that, that's kind of what that is saying. The horizontal asymptote describes the end behavior, what's happening on the far left and the far right, and it's also the same as what we're wanting to do here with a limit. So it has to do with the degree of the numerator compared to the degree of the denominator. So this should be a little bit of a review. If the highest power of x appears in the denominator, nicknamed bottom heavy, the limit will equal 0, just like the horizontal asymptote was equal to 0. This first example, 12, that is the case. We see that it's bottom heavy, and so our limit is equal to 0. Okay, the next one, we are going to come back to this. Let's look at the third rule. This is similar, again, to what we did with our horizontal asymptote. If the highest power of x appears in both the numerator and denominator, so meaning that they are the same degree, the limit is the same thing as what we would do for the horizontal asymptote. So the leading coefficient of the numerator over the leading coefficient of the denominator. So in this next example, that's the case. It's a degree of 3 on the top and bottom, and so our limit will equal the ratio of 4 over 5. We can just write that as 4/5. So those two limit situations are easy. It's exactly the same thing as we did when finding the horizontal asymptote. Okay, now let's think about the top, or the last situation is if it's top heavy. So the highest power of x appears in the numerator. If it's top heavy, the limit is going to equal positive or negative infinity. And all we need to do is plug in a very large number if we're doing the limit as x approaches infinity, or plug in a very small number if we're trying to find the limit as x approaches negative infinity to determine the sign of our answer. Okay, so let's look at example 14. This one is top heavy. So limit as x approaches infinity. And so we're going to think about plugging in a very large number. Something like 1,000 or maybe 1,000,000. If we think about the sign of the numerator and denominator, let's say we plug in x equals 1,000,000. If we do 1,000,000 cubed, it's going to get even bigger. Multiplied by 3, it will get even bigger. That's a really big number. Take away 23, it's still going to be a very big positive number. On our denominator, 4 times 1,000,000, take away 1, it's still going to be a very big positive number. So a positive divided by positive is positive. That tells us that the sign of our answer will be positive infinity. Let's look at this last example. This one is a little different because we have 1 over x on the denominator. Remember that this is the same thing as x to the negative 1. So if we think about the degree of the numerator, the highest power is actually, it's out of order, so it's a 2 here in the middle. That's certainly bigger than the degree of the denominator, which is a negative 1. So this is going to be that top-heavy situation. Something that we can actually do first here with the 1 over x If we are dividing by 1 over x, it's the same thing as multiplying by x over 1. So dividing by a fraction, it's the same thing as multiplying by the reciprocal. So that might be an easier way to think about our function. Also, notice how the limit this time we're finding it as x approaches negative infinity. And so we want to think about plugging in a very small number. Let's actually distribute the x here and rewrite this in descending order. So let's write the negative 5x cubed first, plus 4x squared, plus 3x. So if we plug in a very small number to represent the x values getting smaller, maybe we do something like negative 1,000. So if we do negative 1,000 to the third power, it's still going to be negative. So remember, a negative to an odd exponent is negative. So this is negative. It's going to be a very big number. Multiplied by negative 5, it's going to be positive, and it's going to be a very large number. Okay, added to 4 times 1,000 squared. 1,000 squared is a large number. Multiplied by 4, it's going to be another positive large number. Now we do have this 3x that we're adding at the end, so if we did 3 times negative 1,000, we would be subtracting 3,000 at the end, but that is going to be much smaller than the size of these positive numbers. These are going to be much larger. I mean, 1,000 squared right there, that's way bigger than 3,000, so it's still a very big number. Take away 3,000 is going to stay positive for our final answer. So our final answer for our limit will be positive infinity again. So I wanted to finish by summarizing all of the methods that we've talked about today for finding limits algebraically. If you want to pause the video and grab a sheet of notebook paper to copy down the summary, you can do that and restart when you're ready. So the first situation we looked at was finding the limit as x approaches a, meaning a specific value. First, we tried plugging in the value of a. If that didn't work, meaning if we got a denominator of 0, then we would want to factor our numerators and denominators, cancel any common factors, go back and see if we can plug in a. Sometimes that works. If not, if we still have a denominator of 0, it means that our limit will be infinity, negative infinity, or does not exist. We're going to make a sign chart to see what's the sign of our function, positive or negative, as it approaches our a value from the left and as it approaches it from the right. If it was the same sign, they're both positive, it was positive infinity. If they were both negative, it would be negative infinity. And if one was positive and one was negative, then it simply does not exist. This process will help you with problems number 1 through 24 on the homework. The last situation we talked about is similar to finding the horizontal asymptote of a rational function. The limit as x approaches positive infinity or negative infinity. So as the x values get bigger and bigger, we move to the right side of our graph, or as the x values get smaller and smaller, and we move to the left side. First, if our function was bottom heavy, the limit as x approached infinity or negative infinity would always be 0. Second possibility, if the numerator and denominator had the same degree, the limit was equal to the ratio of a over b, meaning the leading coefficient of the numerator and the leading coefficient of the denominator. Finally, if it was top heavy, then our limit was equal to positive infinity or negative infinity. And to figure that out, we want to think about plugging in a really large number if we're approaching positive infinity to get the sign of the answer, or if we're approaching negative infinity, we want to think about plugging in a really small number. That final list of steps will help us with questions number 28 through 36 on the homework. So I want you guys to try your best on this assignment. I will be posting another video of some of the explanations for maybe some of the more difficult homework questions that you might get stuck on, but I do want you to try all of the problems on your own first. first. So good luck, and I hope that this introduction to limits will help you in your future journey of math classes if you do continue on with calculus.